Hello and welcome to LuckyMath. In this video I want to show you how to graph the logarithm. And I'm again not going to do this by plotting point per point and then connecting these to a graph. I want to show you the big picture of how logarithms look like. And if you've seen my earlier video on this playlist up there, then you should already know how to graph exponential functions. Let this be a coordinate system. This would be the origin 0. And then the function, for example, 2 to the power x would look approximately like this, where it crosses the y-axis at the value 1. So do all exponential functions. And if you would like to have the graph of the inverse of this base to the power x, so in this case 1/2 to the power x, you simply mirror this function at the y-axis, and what you get is approximately this function. So this would be the graph of 1/2 to the power x. If you had the function 3/2 to the power x, you could mirror it at the y-axis and you would get the function 2/3 to the power x. Alright, now what we are interested in is what are the graphs of the inverse functions of these two functions. So the log to base 2 of x and the log to base 1/2 of x. And to do this we always apply a simple trick, which is to graph first the identity map f of x is equal to x, which would be the following line. So this is the identity map f of x equals x, and it is simply a line through the origin at 45 degrees angle from the x-axis. And in order to get the inverse function, the graph of the inverse function of, for example, 2 to the power x, you simply mirror the original function at this particular line, and what we would get is the following. So this is approximately the graph of the function log to base 2 of x. And since we mirror all these points on the other side of the identity map, the log to base 2 of x obviously crosses the x-axis at the value 1, and all logarithms cross the x-axis at the value 1. And you can see that the logarithm approaches the y-axis, but it never crosses it. Therefore, you can only put positive arguments inside the logarithm. Now let's try the same trick for 1/2 to the power x and mirror it at the identity map. What we would get is approximately the following. So this is approximately the graph of the log to base 1/2 of x. And we applied the same trick, but you could just as well also mirror the log to base 2 of x at the x-axis, and you would get immediately to the log to base 1/2 of x. So it's a similar trick to getting from 2 to the power x to 1/2 to the power x. So let's just write down all these tricks. Let's say we have a base a that is real and greater than 1 in this case. Then in order to get from a to the power x to the graph of 1 over a to the power x, you would mirror the function at the y-axis. So this is like the operation, the mirroring, where you mirror your function in order to get from one to the other. So the next trick would be if you have the function a to the power x, the graph of this function, in order to get to the inverse function log to base a of x, you mirror at the identity map f of x is equal to x. And you do the same if you have 1 over a to the power x, and if you would like to get the log to base 1 over a to the power x, you again mirror at the identity map. But you could also, if you already have the log to base a of x, you could mirror this function at the x-axis in order to get the graph of log to base 1 over a of x. Now one last thing, let's graph the exponential function, the natural exponential function where the base would be e, the Euler number that is approximately 2.71828, and it goes on and on since it is an irrational number. So the function e to the power x, and I have a separate video on it up there, would look approximately like this. So this would be approximately e to the power x. And it is steeper since the base is larger than 2. So this is approximately 2.7 to the power x. And in order to get the inverse function of e to the power x, you again mirror this function at the identity map. What we would get is in blue approximately the following. So this is approximately the graph of the log to this same base e of x, and we also call this the natural logarithm, ln of x. So ln is the same as saying log to base e, and I have a separate video up there. So now you can see how the graph of the natural logarithm approximately looks like. And it is flatter because the base of the log is greater. So the greater the base of the log, the flatter the function will get. So this flattens down pretty quickly since the exponential function grows and gets very steep pretty quickly. Alright, enough for this video. Thanks for watching. Rate the video, subscribe, and see you soon again on Lucky Math.